Let's begin and I'd like to talk to you today.
Hello, I'm Johnson Samuel. I am an assistant professor with the Mechanical Aerospace and Nuclear Engineering Department at Rensselaer. I also serve as the director of the Micro Nanoscale Manufacturing and the Materials Design Lab at RPI. My work primarily has got to do with advanced manufacturing processes at the micro nanoscale, and I study the interaction of these processes with advanced materials. Today, I'm going to be primarily talking about an NSF-funded study that is looking at the use of graphene-based lubricants for high-performance micromachining applications. Now, when we use the term micromachining, different people have got different connotations of that word. Let me define what I mean by micromachining for the context of this particular talk. What I'm talking is essentially micro-mesoscale mechanical manufacturing. We also call these technologies as M4 technologies. What do we mean by this? These are basically all your conventional manufacturing processes at the macro scale. So you take processes such as milling, drilling, turning, all of those, and you shrink those down to micro-mesoscale processes. So that means our tooling now might be much smaller than the diameter of your hair. Our spindle speeds are going to be much higher than what is used at the macro scale, so on and so forth. These processes are gaining a lot of significance for the industry here in the United States because they are used for making high-value products. Now, what kind of tooling do we use at these scales? The image that you have on the screen shows one typical tooling, and this one particularly is of a larger size. What you see is a two-fluted tungsten carbide tool. The diameters of these tools could be anywhere between 50 microns to 500 microns. To give you a size scale, 100 microns is roughly the diameter of your hair. The key thing to notice here is the edge of the tool, the edge radius, which essentially dictates how sharp the tool is. In this particular case, it is around 2 microns. And that's typically the edge radius that we see in these tungsten carbide tools. Now, to give you a practical product that technologies like these are used to manufacture, this one here is hard turning of spin bearings. Typically, spin bearings, the size scale that you see compared to the penny on the screen, these are typically ground, but we use turning operations at the mesoscale to actually make the part. And there are two components of this particular spin bearing that are of interest. One is essentially the inner race, which against which the balls push when the bearing is in operation, and the other one is the outer race, which is essentially the cage that sort of keeps the balls in place. The neat thing about this particular application is that when you look at how hard these materials are, they're extremely hard. They've got 65 Rockwell C in terms of their hardness. And when you're machining such hard materials using microscale tooling, there are two things that you have to really take into consideration. One is, of course, the breaking of our tools. Again, these tools could be finer than the diameter of your hair. And the second thing is when you're cutting such hard materials, there's extreme heat, high cutting forces that are produced, so you might end up adding residual stress in the part, which again needs to be carefully monitored. So the way to get around these problems is obviously with the use of cutting fluids, which is what we use at the macro scale also. But now at the scales that we are talking about, the delivery of the cutting fluid becomes the issue, because unlike what you do at the macro scale, wherein you turn on a tap and you let the cutting fluid just penetrate into the tool and workpiece region, at the micro scale we cannot do that, because if we do that particular sort of a delivery, our cutting tools are going to break. And besides, you may not get effective penetration of the cutting fluid into the cutting zone, which are really small dimensions. So the idea is to use atomization techniques. To put it in plain words, it's a glorified humidifier. So we are able to churn out cutting fluid droplets. These droplets could be as small as 20 to 40 microns in diameter. And when these droplets of cutting fluid reach into the cutting zone, they're able to penetrate that tiny interface between the tool and the workpiece and provide lubrication. Of course, there are two things that you have to always watch in terms of cutting fluid efficiency. One is, does it cool the part? Second thing is, does it reduce the cutting forces? The cooling in this case particularly comes from the evaporative cooling of the cutting fluid once it impacts the surface. And the reduction in cutting force comes from the oil content that is there in the emulsion. One thing that we are finding at the micro scale is if we want to increase the lubrication efficiency of the cutting fluid, we have to increase the oil content in the cutting fluid. And what this does is this has a detrimental impact on the performance of the atomizer. Okay, so if you add more oil into the cutting fluid, the atomizer is not going to be able to pump out tiny droplets. So the key is to increase the lubrication performance of the cutting fluid without increasing its viscosity. And the way we are trying to do this is by the use of nanoscale additives. The particular additive of interest is graphene. The image on the slide shows the lateral dimensions of a graphene platelet. Essentially what graphene is these are layers of carbon atoms that are stacked one on top of each other. The lateral dimensions are roughly in the 2 to 3 micron range. The reason why we chose this particular additive is because of its lateral dimension. If you remember, the edge radius of the tool is around 2 microns. So the idea was, would graphene be big enough to just go in and wrap that edge as a blanket when the tool is actually performing the cutting operation? The other thing about graphene which allows us to do this particular operation is the fact that its thickness is extremely low. When you look at the cross section of the graphene platelet, what you find is these are made up of 3 to 4 individual graphene sheets. The overall thickness could be as small as 2 to 3 nanometers. So what you have is an additive which is thin enough to go into the interface between the tool and the workpiece, provide cooling and lubrication hopefully, without interfering with the dimensional accuracy of the part. So we tried this out and we monitored the cutting temperatures as well as the cutting forces that were obtained when we used graphene suspensions. So this data that you see on the screen, it's a plot of the cutting temperature profiles that we see. The blue line there shows the baseline data. The baseline data was off of Castrol Clear Edge 6519, which is a semi-synthetic cutting fluid that was used at 12.5% dilution. We took that cutting fluid and we added to it varying concentrations of graphene platelets all the way from 0.1 down to 0.5% by weight. And what you see is the plot of the cutting temperatures. The thing that you find is the addition of graphene into the cutting fluid drops the cutting temperatures that you encounter. In fact, it's a pretty significant drop. A maximum drop of around 42% was observed. The other thing about these experiments that we found is that graphene outperforms both single wall as well as multi-wall carbon nanotubes. So in that sense, it is a superior additive in terms of reduction in cutting temperatures. The other thing to notice is the cutting force. As you look at this particular graph, what you find is the addition of graphene is again reducing the cutting force as is seen by the first 4 data points. Notice that we are getting around 26% reduction in the overall cutting forces with only an addition of 0.5% by weight of graphene. This again, as you look at the 2 other peripheral data points, what you find is this is significantly better than the single-walled and the multi-walled carbon nanotubes. Of course, we have to look at viscosity trends because that was the main goal of the study. If we increase the viscosity too much, we are back to the same problem in terms of the performance of the atomizer. What you find is that the addition of graphene barely increases the kinematic viscosity of the cutting fluid. In fact, what we see is only a 3% increase in the overall viscosity of the cutting fluid, and this is significantly lower again from the viscosity increase that we see by the use of both single-walled and multi-walled carbon nanotubes. So what this is telling us is we will be able to deliver this cutting fluid through the atomization system without any loss in the atomization efficiency, which is exactly what we were hoping to do at the onset. The other thing that we were interested in looking at is how does graphene change the spreading behavior of this micro droplet as the droplet touches the tool and workpiece interface. And the thing to note there is the contact angle trends. And what we are finding is there is a reduction in the contact angle of the cutting fluid with the workpiece with an increase in graphene concentrations. This reduction causes greater spreading of the cutting fluid onto the surface. In fact, there is a 58% reduction in the contact angle. The ultimate goal of this work is to design graphene platelets for use with green cutting fluids. And one particular cutting fluid that we are interested in is the oil that we get out of algae. Algae is a single cell microorganism that grows in common places like ponds and other water sites. Essentially, it takes in carbon dioxide and converts it into high density liquid through photosynthesis. So in some sense, it is truly a carbon neutral oil source. But right now, if you look at algae oil in terms of a suitable use towards machining applications, it is not there yet in terms of its ability to provide cooling and lubrication for high performance machining. So our goal is, can we engineer graphene platelets? What I mean by that is not only just the lateral size scale and the thickness, but also the chemical functionality that the graphene should have so that it disperses well within algae oil. Because if we can do that, what we hope to achieve is truly the engineering of high performance green cutting fluids, and that would take it to the next level in terms of applications. So we are hoping to get there through this NSF funded project. With that, I would like to thank the National Science Foundation for funding this research, and I would like to thank you for watching.